All right, so on your sheet you have dates and you have assessments, the usual things, and we're about to talk about Unit 8 a little bit. But before I do that, before we say any, solve some more problems on the sheet, I have to tell you this story. It's really, you might even say unbelievable. You might even say unbelievable. Okay, so I went. This is like this really sweet little like indie music shop down in like DuPont Circle area.
Oh, I've been there. Yeah.
Have you been there?
Yeah.
Lots of hipsters coming in and out, and I'm down there. I'm not normally on that scene, but I was like, I just stopped by because it looked like a cool place, and I was paging through records. Of course, we're selling records at this indie music shop, and all this vinyl, thousands, and I just happened to, I was lucky as can be. I just happened to like be paging through these, and then there are lots of old, vintage, expensive stuff, and I look at this and I'm like, wait a second, that can't possibly be what I think it says. And this is what I saw, and the reason that you see it now is because I put it on a piece of white paper in really even light and took a photo for you and put it into this.
Why did you buy it?
Oh, I did, but I have it it's it's at my house. It's a sealed off package.
What did the music sound
Sealed climate control room.
What did the music sound
It sounds really good. You ready to? I think you'll get a feel for the sound of this record as we move on. Okay, let's keep going. All right, the first thing we did was enter into this with like what seems like a very, very simple problem, and I do want to emphasize that it is definitely simple. It rests on something you learned maybe even in elementary school, and that's called the multiplication principle, right? And one way to visualize that is to like use a tree, right? You've maybe used a tree before to visualize this. And it's not the last time that we'll use a tree and use that as like a tool for ourselves. Here are a picture of her 3 shirt, 4 pant, and 2 sock options for shoes. What are they? Socks. Okay. And again, we're not like requiring any matching, or we don't know anything about that, right? We're just allowing for all these options to be available to you. And just notice why the tree is interesting to us. It's because each leaf at the bottom of the tree corresponds to a unique path. If you ended up at this particular branch here, right here, that means that you must have picked a blue shirt and then white pants and then those purple? I don't know what those are. Right? So if each leaf at the end represents a unique like course through the options, then it makes sense that we should be able to, if they're in one-to-one correspondence, we should just be able to count the leaves. And I think you'll find that there are 24 leaves, each representing a unique outcome. And of course, how do you count those more quickly than just numbering them up? You multiply, right? I think it's pretty clear from the picture that you can just multiply to do that arithmetic more quickly. So that's a nice visualization. We can't do that on the next problem we'll look at. But I do want to just underscore again that even though this seems simple, it undergirds everything we're going to do today. Even as they get really, really intense and hard. Don't forget that actually all we're doing is the multiplication principle and things get hairy, okay? So let's take a look at this first one, and if you'll read for us, Alex L., I'll let you. Go ahead.
Policy numbers for a certain securities company are issued in the form Q14327055052, where the first character is a letter and the second character is a non-zero number, and the last 7 digits are numbers. How many policy numbers are available?
Love it. Okay, so already this is not meant to be hard, but I just want to emphasize that like this too is of a similar nature to the clothing problem. Right? So solve it in the next 10 seconds, and then we'll call on someone to share their answer. Keep in mind very carefully the parameters that are mentioned in the problem, obviously. And then when we're ready, we'll hear from
How many letters there were? It's not the Spanish American alphabet. 30.
All right. I'm done giving you time. All right. Alex, do you have an answer yet? Or a method, rather? An idea, at least? Alex, who? All right, listen. Shh. Give us the method. I don't need the answer yet.
Just multiply together.
Multiply some stuff. Okay, so say what those are. What am I multiplying?
26.
Okay.
9. And I guess you would say 10 to the 7th.
Yeah, 10 times more, but much more 10. So let's just quicken that by just saying 10 to the 7th. 26 comes from the number of letters. I think I see that. 9 comes from the fact that we're requiring a non-zero. So we only have 9 options. And then the other ones have 10 options each, right? 0 through 9. So that's awesome. I think that'll work, and it's a huge number. And if you wanted, you could even make a tree, right? It'd be really cool. It would have 26 branches at the top, and then off of each of those you'd have 9, and then off of each of those you'd have 10, and then off of each of those you would have 10 more, and more 10, and then 7 layers of that. It would be a really cool tree with lots of branches. What's that come out to, by the way?
It's about 2.3 trillion.
2.3 times 10 to 9. Okay, approximately. It's a lot. It's still less than the population of the world, though. So I think they're probably not like marketing to people outside the states or something. Maybe they're probably okay for a long, long time. I think they have plenty of ID numbers. By the way, I stole this from my own. This is not my number, my policy number, but
That's not right.
I just trusted someone. Is that not right? I should stop trusting people?
I don't trust you.
Give me your calculator.
It's like a big number.
That is a 9.
That's a 9.
Oh, I thought that was 5.
What's a 9? All right.
9.
Yeah, my insurance company policy is actually almost looks identical to this. I changed it obviously, but it does begin with a Q. So anyway.
So we can figure it out. Yeah, we could.
You can brute force it. I don't think there's even if you knew my account number, I'm not sure there's anything you could do nefarious to me. I don't know, but
We'll just write it everywhere.
information is important. That's true.
Gotta figure out how it'll.
That's right. Knowledge is power. All right, are you ready for the next one? Everyone, think about it if you hadn't already. For another, give me 10 seconds with your group, and then we'll call on someone who thinks they know.
Factorial, yeah.
We're definitely still in the realm of things I think we've thought about before, so I don't think we. All right. You ready? Sorry, discussion over. Luke, tell us what's up. So what do I multiply? What am I doing? What does that mean? I don't know what factorials mean. All right, so 9 times 8 times 7, I hear you saying. Can you justify why you're doing this? You're going to do more.
You can't use that digit again.
Okay. Yeah, you're kind of filling these 9 slots you have available to you. Right, you're kind of filling these 9 slots. The first slot you have 9 options, but then after that you only have 8. I see what you're saying. So all the way down to 3 times 2 times 1 if you like. And then you gave a more efficient way to say that then. What did you call it? 9 factorial. Maybe you've seen that before. We write that. We do that. We're going to end up doing that so often that we give that a nice notation. If you're not familiar with the factorial notation, now you are. It's 9 factorial, not 9. Right. Okay. And that comes out to something large. Do you have it?
It's 362,880.
362.
880.
880. Okay. Eric, go ahead. Sorry.
I got it. I was wondering if I could do on the calculator.
Good. On the calculator, can you help your neighbor too? On the calculator, it's math,
Herb.
and then go over to the PRB menu, and it's number 4. Is that right? All right. So make sure you know where that button is. It's much faster than actually typing that out, right? So in general, if you're arranging 9, excuse me, guys. Thanks. If you're in general, then, if you're arranging n objects of any kind, whether they're numbers or whether they're people in a line, you have n people in a line or n whatever, then the number of permutations of those objects is what? N factorial, right? There it is. And you just proved that, again, this is like, ooh, we're getting into interesting results now. Well, no. I mean, yeah, but It's also just still the multiplication principle. Like at every turn today, as we do something new, we're going to say that again. It's still just the multiplication principle. So do this if you haven't already, and again, I'll give you 10 seconds. No. I don't think I did. All right, fine. I don't know. Sorry. Sorry, I'm being a little pushy. Let's do this one first. I'm here always. Okay. Pushy. You only get 5 more seconds. 4, 3, 2, 1. All right. So what's the answer to that one? I don't mean it to be any different or anything. It's just practice here. Eli, give it to me. Pushy. What is it?
Wait, how many letters are there? 5.
You don't even have to give me the number, but what do you do? It's not a trick question, don't worry. Sorry, maybe I was being a little too.
So it's 5 factorial.
And maybe we do know what that is. We can do that in our head, maybe.
Yeah.
4 factorial is 24 times. Yeah, it's 120. All right. Moving smartly along. Now here we are, Justin. We're ready for you. All right. I'd like you to think about this, and this is again maybe under the same umbrella of the things we've been talking about. So I don't think I need to say too much about it. We'll just like refresh our memory on how this goes. Go ahead and give this one a try with your team, and I'll call on someone in 10 seconds. Who's going to get this one? Who's it going to be?
Oh.
Great. You be ready?
Yeah.
I believe you. All right. Are you ready? We're going to hear from Grace Z. You don't need the answer yet. Just tell me what you're doing. Listen, you over there. Did you hear that? Did you hear what she said? Say it again, Grace. Did you like that? 20 times 19 times 18. And actually, did you compute it, Grace? I don't. 6,840. Did I get it right? Okay. All right. So do you guys agree? It sounds like that didn't shock anyone. Good. Is there another nice way to write that? Like, especially if I had asked you like to do this with 7 different awards, say, then this becomes cumbersome a little bit to be like 20 times 19 times 18 times 17 times 16 times. Is there a quicker way to do this? Do you see anything in the? I mean, this feels a little bit like 20 factorial, doesn't it? Except not. Yeah.
Well, I don't know, but I'm guessing how I would write it would be like the exclamation point divided by 3.
Divided by 3.
Or no, the exclamation point.
Is it over?
I like the idea of dividing by something.
Is it over 20 minus 3?
Don't you put it over 17?
Yeah, it looks like this is like 20 factorial divided by 17 factorial. Absolutely. All the people were saying that. And just to make sure that we're bringing everyone along, do you see it? You will in a second. Okay, that's 20 times 19 times 18 times 17 times 16, etc. by definition, and this is 17 times 16 times stuff, etc. by definition. And all the other stuff cancels out, leaving us with the desired thing. In this particular case, that's probably like more power than we need, but it does provide for us a nice generalization. If you have n things that you want to take r at a time, then in general, what might you do? If you have, again, my first guess is n factorial, but then what do I need to do? Over r factorial?
Over n minus r.
Over n minus r factorial, right? There it is. There's the formula. And again, let's be clear. Even though we just moved into the realm of giving like, oh no, a formula. Let's not forget we are still just doing the multiplication principle. At every turn, why did you reason to this? Well, from the multiplication principle. Still, it's just a compact mathematical way of doing that. The way you might write that is this is your calculator's notation, and this is how people will often write it. As a little n and then a big P and then a little r. That's n things permuted, r of them at a time. On your calculator, you'll enter that if you want it, again, a little overkill on this problem up here that we just did. But in the future, if we get really big numbers and it gets messy, then this might be handy. If you want to do 20p3, which is this problem, on your calculator, you'll go to that same menu. Type in 20 first, and then go to Mac, your PRB menu number, whatever. What is it? I don't know. Go to NPR, and then come back to your home screen and type 3, okay? And just verify that your calculator is working. Did it get 6,840? Wonderful. You can also type in 20 factorial divided by 17 factorial on your calculator. All those should give you the same answer. All right, so I don't have much more to say about that formula. Like, I'm done being interested in it right now. I'd like to turn our attention to this problem, which right away I'd like you to really, before we even answer it, I'd like you to kind of think about with me why this is even a tricky problem and why this is actually worth taking some time to pause and really, really think about. Yeah.
Because you have to exclude it where you're switching.
Yeah, this just feels like the pushy one that we did a minute ago, but we've got this like repetition of p's that's going to cause us some trouble in life. So how do we deal with that? My first instinct is still to say 5 factorial, and then that's my like knee-jerk reaction. But then can we adjust for that somehow? It's clear that I've overcounted somehow. Like that counts way more arrangements than we actually meant to count. So I'm gonna start writing them out here. Are you ready? I'm gonna start writing them out, and I do want your input in a second. I'm gonna write them out, and I'm gonna write them out as if they're labeled and as if they are different. Like this would be the number of arrangements of pushy too. So I'm gonna label them with subscripts. Here they all are, all 120. If you can imagine these triple dots keep going on to the right of the board forever here. Not forever, but until we get 120 in this list. And all of these are different. All 120 are different if you take into consideration my subscripts. Now I've grouped these in a nice way, haven't I? You see it? Because all of these are different in this first column if the subscripts are taken into account. Do you see what I did here? Like this one, this first one is different than this one because P2 and P3 are permuted, right? But, of course, why did I sort it that way? If we take away the subscripts, what do we have in this list? We don't have 120 anymore, do we? Again, you have to imagine the entire list here. What do we have? And how far off are we? And how do we get the answer? How far off are we? If I've sorted the list correctly here.
Oh, I wasn't going to answer the question.
Well, I don't want to hear from you then. No, sorry, I'll come back to you in a second. Sue, ready? Go. Okay, it looks like first thing to say is we're off by a factor of something. Keyword factor. We're off by like a multiple of something, right? Like we've overcounted by a factor of, well, if you trust my work, then I've overcounted by a factor of 6, right? And there they are. In that column, 5 factorial is a number that counts that column as being 6 different things, but we don't want to count those all as, we want to count those as one thing. So in general, we just want like the first column here. I don't know how you want to say that. In general, we just want 120 divided by 6. Now, Sue, you already gave away the other part too. Where did my 6 come from? How did I come up with 6? Yeah, there are 3 P's. How many arrangements are going to be in this column? If we fix U and Y, then our only choice remaining is where do the P's go? And there are 6 ways to do that, right? 3 factorial ways of arranging 3 P's. So does that make sense? So even though you do still have to think about that along the way. I think that's interesting. Sorry, okay, I'm ready for you, Eric. Go ahead.
I was going to say that I think it would be easier if you just imagine these pieces as blank spaces.
Okay.
You're just moving around the U and the Y.
Well, then you're tempted then to just be like, oh, I see what you're saying. But then we haven't really talked about how to do that maybe. How many ways can you put U and Y in 5 blank spaces? I don't know.
I mean,
How do you do that?
put one in the next space.
And then put the other, and then you have to put one in the next space and do the other, and then.
It's basically 5 blank spaces.
I would just like to see your work. I mean, there's definitely a way in on that, and I like it a lot actually. But I'm interested to see how you're going to do it because I think you're right. But so this kind of bridges us on the notion of distinguishable permutations. That is, permutations that we like count the same or count the different. So if you have n things, in the last case it was n letters, 5 letters, then the answer is it's 5 factorial. But wait, we need to divide by the number, and we only had one thing repeated last time. But for each thing that's repeated, we need to divide out by that thing, however many times it appears, factorial, right? So in general, it might look like this, right? You're going to divide by all of those things, and we want to do bumblebee next. Do you see where we're going for this? You see that the issue here, we have other things repeated, don't we? 5, 6, 7, 8, 9. So my first guess is 9 factorial there. But then I think I'm off by, again, by a factor of something. So I need to divide by some appropriate things. So, again, I'll give you 10 seconds to do it. I mean, 20 is what I meant. 20 is what I meant. And we'll get someone here. Nope, don't want to talk to you. Oh, that's a good person. All right. Again, let's not like ever lose sight of the fact that we're still just doing multiplication principle all the way down here. Rachel, when you're ready, I'm going to come to you. Just see. Yeah. Whenever you're ready. Don't give me a number. Give me the calculation you're doing.
Oh.
Are you ready?
Yeah.
Okay, I'm ready.
Factorial divided by 3 factorial times 3 factorial.
Okay, good. And this is just you showing that you understand what we just said and that you understand the implications of that formula. We're just doing for everything that appears. Now, wait a second. I think I understand where the 3 factorial came from. That's the number of times b is repeated. Got it. What about the other 3 factorial? Okay, I got it. There's a second thing repeated here. What about the u, though? So don't we have to divide by 1 factorial also? Okay, so you did that already. I got you. And what about the L? Yeah. So you can do that if you want or not. Doesn't matter, right? Yeah.
Does doing 3 factorial squared work?
Sure. I mean, absolutely. In this particular case, since it's 3 factorial and 3 factorial, you could do that.
Would you have to put them in like parentheses and stuff?
Yeah. Actually, I don't know. I think actually it'll take precedence. I don't think you actually have to. When in doubt, put parentheses though, but I don't think you actually have to. What does that come out to be? 10,080. Okay. And others agree. So you see how that's going to work, right? Moving smartly along. Boom.
3.
Huh?
3.
What?
Just really excited 3 is in the last one. Instead of 3 factorial, 3 factorial.
Oh.
Sorry.
All right. How many arrangements are there for the word word? So that we either start with an O or end with an O. So discuss that with, even though we haven't talked about a problem of this type yet, I'd like you to just launch into the table again. Give you another, I'll give you a total of 15 seconds to talk about this one. 15 seconds.
Because it's O. O is that stuff given. And you have WRD. Oh, no, it's added. It's not
And actually, it's more complicated, Eli, for negative. The real quantities are very, very exponential. All right, I'm ready. That was way more than 15 seconds, but I got pulled into a really interesting conversation. All right, Sue, you want to tell me how you guys came out on that one? So word, this one here, the word one? Yeah. Whatever that's called. Listen. Sorry.
So after much deliberation, I decided to use 2 different probabilities and then add them together.
I don't know what you mean by probability, but I'll keep going.
So one of them starts with 0 and then the other one ends with 0. So it's
Oh.
oh.
It's all right. We're being critical, but you're doing an awesome job. Keep going.
So the first
I get you.
can only be 1, so it's 1. And then the second then the other one is 3 times 2 times 1 times 1.
Okay.
And then add them together and it's 12.
So this is the number of ways of, if I force you to have O at the front, the number of ways of filling the other 3 spots with the letters W, R, and D is 3 factorial, right? The number of ways of assigning 3 things to 3 slots is 3 factorial. And the number of ways of doing this is 3 factorial. And she said we can add those up, and we get 12. Did everyone get 12?
Yeah.
Good job. Okay. So that would be one way to say it would be it's 3 factorial plus 3 factorial. And you've kind of highlighted the thing I wanted to mention on this slide too, especially, right? So we have the situation where we're either, and I think this is the key word here, either you have the O at the beginning, and here's the key word, or you have it at the end, right? And with like a little bit of like grammatic footnote on that, generally speaking, like will correlate to a plus. We'll see that, or a sum. That being said, could you solve this problem using strictly the multiplication rule? Like, yeah. It's also 2 times 3 factorial. So what's the tree look like when we interpret it in terms of multiplication here too? Well, the first branch of the tree would be you deciding where the O goes. That's your first decision as you wake up in the morning. Where am I going to put the O? Right? And then after you've settled on that, then you have 6 other decisions, 6 other options to make off of those branches, right? Can you picture the tree that goes with that? With at the end 12 branches, 12 things at the end.
Wouldn't 4 factorial divided by 2 also work? Because like you have 4 spaces.
I like that, yeah. Yeah. It just so happens that this is the ones we want are equal in size to the number we don't want, but so that's maybe a coincidence. But all right, and then if you haven't looked at this one here yet, you should. And maybe you have taken a chance. By the way, it's very convenient, the names I'm using here, right?
Yeah.
So what we don't want to have happen is Daniel, we don't want to have Daniel be here, right?
What? No, you want Daniel to be here.
No. We don't want you to be last. We don't want Daniel to be last. That would be bad. Yeah, see?
I
Okay.
don't even need you guys to talk.
So you can think of all the ways that could happen. We don't want that to happen. So what's a good computation here? I mean, I feel like we just worked through this, right? Where could Daniel be?
Not
Daniel could be here. Daniel could be here. Daniel could be here, and that's it, right? So this feels like the same problem a little bit. What is it going to be? 3 factorial plus 3 factorial plus 3 factorial. Right? Very similar to the last one. And that comes out to 18. Do you have a slicker way to do that than what I just did? Yeah.
You could say that you know there are a total of 4 factorial possibilities, and 3 factorial of those possibilities you're not allowed to have. So 4 factorial minus 3 factorial.
Yeah, I kind of like this, and this will become handier as we get into problems where like this would save us more time. Here it doesn't save us that much time really, but does it make sense, his calculation, and why that should come out to 18 also? Right? Because 4 factorial is the number of arrangements of these 4 people without any restriction. And then we just need to subtract off the one case that we care about, the one we didn't think about, and that has 3 factorial arrangements. You see where that comes from? Beautiful, right? By the way, it makes me think, does that mean that 3 factorial plus 3 factorial plus 3 factorial plus 3 factorial is equal to 4 factorial? Or that in general n minus 1 factorials sum to n factorial? Is that always true? Like if we do 4 factorial plus 4 factorial plus 4 factorial plus 5 factorial, can we get 5 factorial? Prove it, right? Yeah. All right. Let's talk about symmetry. Like I said, we're stepping this up a notch every time we go here. We're already getting in hotter and hotter water here, aren't we? Okay. Let's talk about symmetry. How many ways are there to see 7 card players around the table? Before we answer that, let's just like all come out and say why that's even interesting. Why is that even trickier than our previous questions? Thomas.
Is it a round table?
Sure, but even if it isn't, I kind of don't care because we're playing a game. So Can you tell me why? Let's say it's round.
Fine, that'll get better percent. So,
Yeah,
because if you rotate the 7 around one position in the table, then it won't have any effect on the game.
Right, it's still the same game. You still discard to the same person. You still receive from the same person. Let's take a small case with 4 players. With 4 players, that is to say, if you and I played cards last night, you and me and 2 other friends of ours, we played cards last night, and this was our arrangement. A in this seat, B in this seat, C in this seat, D in that seat. And then tonight we're like, okay, let's switch things up, guys. Let's do this arrangement. Everyone should be like, oh, wait, that's not really different, right? It's the same arrangement we're talking about around the table. I'm still discarding the same person. I'm still receiving cards from the same person. Or for any game, actually. It doesn't matter what. B, C, D, A. What else? C, D, A, B by the same logic. D, A, B, C. All those we want to count the same. So my first guess on if there were 4 players would be 4 factorial, right? But we've overcounted by a certain amount. If there were 4 players, we're doing 4 factorial. I didn't list them all out. There's this long list, triple dots here, right? A long list. Yeah, you want to take a seat?
Yeah, so we divide by 4 because there's 4 rotations.
Yeah, each one of these, like imagine me writing out all 4 factorial of these options. Every 4 of them has this property that they're the same really to us. Yeah, exactly. So over here, what are we going to do, you think? Maybe 7 factorial divide by 7. That's also known as 6 factorial, which is also known as 720. Right? Okay. Okay, and then now we've got keys to think about. So 8 keys. I see you're already saying what that is, maybe, right? You're already thinking about it. But I need you to look at some keys before you get too carried away. You can do, yeah, there's another sticking point on this one. Say it again, Justin. You can also flip it. That's something you can't do with the people around the table. Okay? We don't consider that arrangement to be the same when everyone's upside down, okay? But with the keys, if I do this and then I do this, you're going to be like, that's the same, right? If you take them all off and then restring them on this way, the flipped way, and then put them painstakingly back on, I'll be like, I could have saved you time. Right? So we would consider those maybe to be the same if I don't even have to take them off the key ring. So let's go over here to 4 the 4 keys case, just because it's easier to write out maybe. Okay, with 4 keys, that is to say we still want to think about rotations. I'm going to write these all again. We like rotations. Those are all still options for us. But what else is the same in this new case? What else is the same arrangement? Yeah, that is a reflection here. D, C, B, A cannot be gotten by simply rotating these keys, right? But it can be gotten by a flip of the keys. So we're going to consider that also to be the same, because we could just do that. And each one of these has a reflection that's not on our list yet. A, D, C, B, B, A, D, C, C, B, A, D. All right, so again, there are 4 factorial. Imagine there are 4 factorial in our whole list. So how much have we overcounted by this time? It's 4 factorial divided by what? 8, right? There are 8 that are all actually the same for the key situation. Again, we can't do this whole flip over thing up top. So over here, what do we think it is? 8 factorial divided by 16, or in general, like if we have n keys, it might be n factorial divided by 2n or something. We have to be a little careful about that, though. You'll maybe think about it. So what does that come out to? I don't know.
2,520.
2,520?
Yeah.
All right, and then a startling result that we should talk about, too, is this one I have holding in my hand. Right now I have 3 keys to my hand, so do the result again for 3 keys. What do you get? 1. Wait, that can't be right. Really? Yeah, really. Yeah. So I can do this, right? I can flip them like this, and I can also turn them like this. Right? I can rotate and I can reflect. So my challenge to you, if you don't believe that there's really only one arrangement for these 3 keys, is I'll throw them to you. You take them off. You put them on any way you like, and then you throw them back to me through the air, and I catch them and I say, I don't think you did anything. I think you did nothing. Because any arrangement you can make, I claim that any arrangement you can make with these by taking them off and putting them back on, I can just do by doing this kind of stuff, right? Right, so I can do flips and rotations. Well, yeah, so that was the footnote I had here. What's going on with two keys? Think about that. I don't want to answer that right now, okay? This is like a deep, deep area. We could go really, really far into this, right, with symmetries. These problems could get really complicated if you thought about it. Like the only paper I've ever had published in like an actual journal is a paper answering the following question. It's like one of these, okay? And the question's easy to ask, but the answer is really, really difficult to obtain. If you have an icosahedron, which is one of the 5 platonic solids with the one that has the most number of sides, it's 20 equilateral triangular faces. Have you seen that before? It's beautiful. So it's perfectly nice and symmetric and everything. And then I say, you are welcome to paint. The question is, how many ways are there to paint the icosahedron with one of 3 colors on each side? Can you imagine how hard it is to understand, like, when you painted it one way and you painted it another way, and to decide whether your 2 are the same is very difficult in that case, right? So not obvious. It takes a lot of work to work through. So anyway, the point is these questions, in fact, just in general in combinatorics, it's super easy to ask like innocent questions. Like, how many lock codes are possible on my Android phone? Swipe patterns can I have? Or how many, right? Innocent question, but like impossible to answer. Yeah. All right, arranging things together. Let's start throwing things in bags. Okay. 3 science. We got. If you've looked at this already, we're arranging some textbooks here. And we're arranging some textbooks, and let's be clear, these are different science books. I've got 3 science books from my years taking science. I got a biology and a chemistry and a physics book or something. Okay, and then 4 mathematics textbooks that are all different, and 5 history books that are all different. How many ways are there to arrange them on the shelf such that, because I'm OCD, the subjects stay together? Please, come on, right? Naturally, we want them to stay together. So, what do we do? I don't know. If you're thinking about choices and trees, my first choice in life might be deciding where the subjects go first, right? Am I going to do, this is like soul-searching question, am I going to do like science, math, history, or math, history, science, or history, science, math, or how many ways are there to make that choice? That is, yeah, there are 6 ways to do that. All right, now I'm done with that choice. Now what do I have to decide? Now that I've settled like where are my labels on the shelf, science, I made a label maker thing, math, history. Now that I've settled that, now what? Now I'm over in the science section, and what do I have to do now with my 3 science books? I have to arrange those. 3 factorial ways to do that after already having made the other decision. And then likewise for the math books, 4 factorial times 5 factorial. And that equals something, I don't know what, something, you can figure it out. So my way of picturing this might be to say, let's throw the books in a bag, right? Can you imagine, like in a sack? First we arrange the sacks, the 3 sacks, 3 factorial ways to do that, but then we have to take the books out of the sack and arrange them, right? So how do we do this one down here? We've got, when we do a 5-person family, but we require mom and dad to sit together, just for the sake of, marital harmony or something, okay. How do we do this? Again, let's think about bags here. You're the 5 people in the family. 1, 2, 3, 4, 5. This is mom and dad, say. So we need to throw them in a bag. Throw mom and dad into a bag. Okay? And then each of the children get their own bag. They're all in bags too. Okay. I know this sounds bad, but it's going to be wonderful in a minute. Okay. We arrange the bags. How many ways are there to do that? There are 4 bags. What does that come out to be? 4 factorial ways to arrange the bags. Then we remove the bags once we've settled on where the bags are going to be. But then we still have to arrange mom and dad, right? So 4 factorial times 2 factorial in this case is all, which the 2 factorial is of course just 2. And that comes out to 48. Did anyone tell me what this first one was? 3,000. Look at that. Look at that. All right.
No, wait.
All right. We did very well today. That was good. There's more tonight. There's so many interesting problems here. I don't even know what to do. Also, what'd you say? This is not right still? Thank you. There's an interesting fact up here for you on the way out, too. This is kind of fun. Too. Bye, everybody. I told you it's not going to be good, right? I haven't